talking about the motion of charges across a magnetic field.
All right, in this example, we're going to explain the principle of electrons. Principle of why electrons are deflected in the magnetic field. In this example, we have block A and block B. As you can see written in this example, block A is going to be attracting the electron and block B is going to be repelling the electron. Now, when the electron passes block A and block B, the electron will flow in the direction going to the left, and then also make a jet direction to the right. Two blocks A and B are representing of dipole. All right, and this right here is going to be our example 2. In our example 2, block A is going to be now repelling, and block B is going to be attracting. And when we do this, the magnet will flow through both block A and block B, go in the right direction, then take a turn for the left direction. And this is also another example of block A and block B representing the dipole.
Now we'll be looking at the motion of an electric charge in a magnetic field. Let's examine the motion of an electric charge in a uniform magnetic field. Because the magnetic force depends upon the cross product of the charge velocity and the magnetic field, the motion is usually three-dimensional. We will start with a special case where the initial motion is perpendicular to the magnetic field. In this case, the resulting motion will be confined to a plane perpendicular to the field. Since the force and hence the acceleration is always perpendicular to the velocity of the charge, the resulting motion of the charge will be circular. The force on a negative charge will be reversed compared to a positive charge of the same velocity. As a result, positive and negative charges reverse their circles in opposite directions. Speed also affects the radius of the circular motion. However, the time it takes is not affected by the speed. The frequency of orbits only depends upon the charge, the magnetic field strength, and the charge's mass. Returning to the more general 3D case, the net motion of the charges will be determined by the parallel and perpendicular components of the charge velocity relative to the magnetic field. The component of velocity parallel to the magnetic field determines the part of the motion along the magnetic field lines. The component of velocity perpendicular to the magnetic field determines the circular motion around the magnetic field lines. The net result of these two motions is a helical motion where the charges spiral around the magnetic field lines.